We write a function by typing in the word function, followed by a variable name for the return value, then an equal sign, the name of the function, and parameters in parentheses. This is followed by the body of the function. In this case, we want the result to be the product of value and image. To ensure that we are performing element-wise multiplication, let's change the star to a dot star. This doesn't make any difference when one of the values is scalar. But when the two quantities being multiplied are vectors or matrices, then star and dot star produce different results. We end the function by typing end function. Let us load an image and try out this function. And there's the scaled image. Now that we know how to add two images together and multiply image intensity values by a scalar, let's revisit our example of averaging two images. We saw that division by 2 can be rewritten as multiplication by 0.5. Now this results in an image which has equal parts dolphin and equal parts bicycle. What if we wanted to change these ratios? Say we want more of dolphin. But note that in order to keep the maximum intensity value the same as that of the original images, we should ensure that these weights sum to 1. In general, this is known as blending two images. Let's see what it looks like. Yes, we do see a little bit more surf from the dolphin image, but it's a little hard to tell. How about we change the weights a little further? Ah, more dolphin. I wish we had a function to do this, which we could call like this. Can you write this function for me? Let me get you started. Put your code inside the function body. Remember, to return something, assign it to the output variable. Also note that A and B are the two images to be blended, and alpha is the weight to be applied to A. Once you have implemented the function, test it out with different values of alpha. We know that we want to multiply A by alpha, and since the sum of weights needs to be 1, we multiply B by 1 minus alpha. And finally, we assign this to the output variable. That's it. Let's see what we get. Alright, same image as before. Now see how easy it is to change the blending weights. For example, I want little less dolphin and more of bicycle. And there we go. It almost looks like there's water on the street. This method of obtaining a weighted sum of two images is the basis of alpha blending.
So if images are just functions, then we can do things to images that we can do to functions. Like we can just add them, right? You can add two functions, right? Well, then we can add two images. And to introduce this a little bit, we're going to introduce the concept of noise. Okay? So noise in an image is just another function that, combined with the original image, gives us a new function. So we'll just write this way as our new image, we'll call it I prime, is just I of xy plus this noise function. Well, what does that mean? Well, we have to take a look at what this noise function would be. Okay, so there are lots of different kinds of noise functions. Here's one, and this stuff is courtesy of Steve Seitz. There's a type of noise called salt and pepper noise, which doesn't take a rocket scientist for you to figure out that probably what it does is it takes your original picture and it sprinkles occasional white spots and occasional dark spots. And that's called salt and pepper noise for the obvious reason. A relative to that is something called impulse noise, where you just get little white specks now and then. Different kind of imaging systems might give you that kind of noise. But by far, the noise that you're most familiar with is typically Gaussian noise, or normally distributed noise, where we basically assume that at every pixel we take the original image and we stick on here some value that is independent, identically distributed from some normal or some Gaussian distribution. All right? And that's Gaussian noise. And most of the time, when we talk about noise, we'll talk about that function. Okay? We can actually have MATLAB make us a noise function. It's real easy. So here we say, look, we're going to make a noise array, which is just, I take the size of my image, rand n generates a noise signal that has a mean of 0 and a standard deviation of 1. And if we scale that up by some sigma, okay, that will spread that out and make it bigger. So that's essentially a noise with mean of 0 and a standard deviation of sigma. And because functions are just functions and images are just functions, I can just add them. I can say let my output just be the image plus the noise. And if I were to plot that, you would see what's here, right? And on the right, you can see that there's all this noise in our peppers. And if we plot this, you can see here we get this nice clean plot. And here we have all this extra noise that's been added. And so that's our noise function.
If you can add two images, you can subtract them as well. The difference between two images is simply one image minus the other. It might be hard to understand at first what's going on. Greater values in a difference image signify greater difference between the two images. Brighter areas in this result indicate where the two images differ more. Note that this is dolphin minus bicycle. Here the order matters. Bicycle minus dolphin gives us a different result. This makes sense, as what the difference operation is doing is simply subtracting pixels in corresponding locations. If two such pixel values are A and B, then A minus B is different from B minus A. But when thinking about the difference between two images, we often don't care about which one is greater and which one is less. Note that B minus A is simply A minus B negated. When thinking about the difference between two images, we often don't care about the sign of this difference, only the magnitude. That is, we're interested in the absolute difference between two images. For that, you use the octave ABS or ABS function. Let's see how different the two results are. Wait a second, these two don't look different. In fact, they're exactly the same. What's going on? Let's take a closer look at our code, especially this line. Let's say two values being subtracted are 20 from bicycle and 56 from dolphin. Theoretically, the result should be minus 36. But remember uint 8? These images can only represent numbers between 0 and 255. So what happens here? It gets truncated to 0. Notice that even in the absolute difference case, the subtraction is performed first. This intermediate result is the same as the original difference. The numbers here are already between 0 and 255, so the absolute value operator doesn't make any difference. So what can we do about this? So we're losing out all the negative values in the result. How do we ensure that we can preserve image difference? Let's say A and B are two images of type uint 8. Check the following options which you think will give the desired result. For instance, should we compute the absolute values of the two images first and then compute their difference? What about this expression? Or converting to a different type? Would that help? The first expression doesn't make any difference. A and B contain only positive integers. So this will give us the same incorrect result as before. The second expression is interesting. A minus B would give correct difference values where A is greater than B and 0 where B is greater than A. Similarly, B minus A will give you correct difference values where B is greater than A and 0 where A is greater than B. Hence, their sum is in fact the absolute difference that we want. Converting the images to uint 16 does increase the range of values that they can store. But remember that U signifies unsigned, which means uint 16 cannot represent negative numbers, and we'll end up getting the same result. Floating point images can inherently store negative values. Hence, converting to floating point would help. Fortunately, there is a built-in function to compute image difference that preserves values. We don't have to explicitly convert the data type or use any funky expressions. This function is contained in the image package in Octave or image processing toolkit in MATLAB. You can load a package by typing pkg load followed by the package name. The function we want is called imabsdiff. It takes two parameters, the images to be subtracted, and the order doesn't matter. Let's see how this compares with our previous attempt. As you can see, this preserves the magnitude of image difference throughout the image. The image package provides many more functions to carry out common operations. Feel free to explore them. So we know that rand_n generates Gaussian noise. Let's see how it actually works. If you call rand_n without any parameters, then it returns a random number. Here we get 0.76388. Run it again. A different number, 1.3958. You can pass in dimensions to rand_n to generate a vector or matrix filled with random numbers. Let's say we want a row vector of 5 columns. So 1 row, 5 columns. Each time we run this, we get different sets of numbers. As you might have guessed, we can generate a two-dimensional matrix of random numbers as well. Say we want 2 rows and 3 columns. Since these are a bunch of random numbers, we call this noise. What is interesting is that rand_n draws these numbers from a Gaussian or random normal distribution. Hence the n in rand_n. A Gaussian distribution has a probability distribution function that looks like this. The center or mean for rand_n is 0 and the standard deviation is 1. The standard deviation is a measure of how spread out the distribution is. I mentioned this is a probability distribution, which means getting back numbers that are close to 0 is highly likely, whereas numbers far away from 0 are less likely. How do we know for sure that rand_n is actually sampling from a Gaussian distribution? Well, if we had enough samples and distributed them among bins, and we counted how many numbers landed in each bin, then we would see a pattern similar to the probability distribution function. Let's try that. How about we start with a vector of 100 numbers? Instead of displaying the numbers directly, let's compute a histogram. Hist accepts a vector or matrix of numbers as the first argument, and as an optional second argument, you can pass in bin centers. Let's say we want the centers to be integers from -3 to +3. Hist returns two values. One is the count of elements, which we want, and the second is the bin centers. Let us display the bin centers and the counts in a tabular form. We'll create a small temporary matrix, with the first row being the bin centers and the second row being the counts. As expected, the center has a high count and the ends have low, in fact 0 counts. You see the same behavior no matter how many times you run it. For a visual representation of what's going on, how about we plot these numbers? X-axis will contain our bin centers and the counts will be on the y-axis. We see something that vaguely resembles the Gaussian probability distribution. To get a better picture, we need more bins. You can generate a sequence of uniformly spaced numbers using the linspace function. Here we can replace this vector by writing -3 to +3, 7 different numbers, that is including 0. Let's make sure this is the same as before. Note here that the bin centers are same, as expected. Now we can easily increase the number of bins. Say we want 21 of them. I'm going for odd numbers because I want to include the 0 in the middle. Displaying so many numbers wouldn't be useful, so let's comment that out and see what the plot looks like. Clearly we have better resolution along the x-axis, but what's going on with these spikes? I think we need more data. Let's bump up the vector to 1000 numbers. Now you see the familiar bell curve slowly emerging. Let's increase the number of samples further. There you go. In addition to rand_n, you can find other random number generation functions in Octave or MATLAB, such as just rand. This samples numbers from a uniform distribution. rand_i generates random integers. Feel free to play with these functions.
So I just snuck one past you there. Okay. We said the magnitude of the noise is determined by sigma. Fine, that's great. In fact, we could just look at the noise function itself, right? So don't add it in the original image, just look at the noise function. But we can't do that just yet until we make a decision. And the reason is this. What's the mean of the noise? Megan?
0.
Oh, very good. So that means some of the values are going to be what? Positive. Some of the values are going to be negative. how do we look at a picture that has positives and negatives in it, right? If we said 0 was black and 1 was white, or 0 was